Hello. In this lecture, I am going to work homework problem number 6 from section 4.5. I hope that you will try it on your own first, but typically some students have trouble with this problem, so it's a good example to go through. So we're asked to basically sketch the graph and label the important points such as extreme values, inflection points. So we have that list of questions that help guide us when we want to do this. And I've got some of them here. So we want to find the domain. We might check for symmetry because sometimes that can be useful. Then we'll find the first derivative, get the critical points, find the extrema, etc. So first, let's talk about the domain. Of course, this is a polynomial. So my domain is all real numbers. And let's talk about symmetry. This function, if you plug in negative x to this function, what happens? Well, I'm just working it out to see. So I plugged in negative x, and notice what happens. So f of negative x equals f of x. This means this is an even function. It has y-axis symmetry. Okay, so let's now find the first derivative and determine where the extreme values are. And notice that this is a fourth degree polynomial with a negative leading coefficient. So my end behavior is down on the left and down on the right. So I'm going to find my derivative. I'm going to need a little more room. So I'm going to go ahead and factor this. I will pull out a negative 4x. That leaves me with x squared minus 1, which I can further factor because that's the difference of squares. So what are my critical points? X equals 0, x equals negative 1, and x equals 1. We have 3 critical points because we have 3 factors there when we set this equal to 0 and solve for x. So I'll set up my test intervals down here. Negative 1, 0, 1. And we will look at this factored form of the derivative and test a value in each interval. So I might as well use negative 2 here. We have 3 factors. If you put negative 2 into that first factor, it is positive. Put negative 2 in the second factor, which is x plus 1, that is negative. Put negative 2 in the third factor, and that is negative. So my derivative is positive in this first interval, which means the original function is increasing, which agrees with my end behavior up here. original function. Okay, test something in here like negative 0.5 or negative 1/2. Again, that first factor will become positive. The second factor is also positive. The third factor will be negative. When I put negative 1/2 in there, that is negative. So overall, my derivative is negative in that interval, and so my original function is decreasing. And this is a max. We can see that. Okay, now let's test positive 1/2. Put that in the first factor, it will be negative this time. Second factor is positive. Third factor here will be negative. So overall, my derivative is positive and my original function is increasing. So this is a minimum at x equals 0. One last test interval we can plug into our three factors. The first factor will be negative, then we have positive and positive, which means my derivative is negative, so my original function is decreasing. So this is also a max. Now, remember, this is a fourth degree polynomial, and it's opening down, so it's going to have an absolute max. So this is the absolute max. And how do I know that? Well, because I've already worked the problem. But these are, and we have symmetry. Whatever this f value is going to be the same as this f value. So what is f at 1? Well, that would equal negative 1 plus 2 minus 9. So f at 1 equals negative 8. And f of negative 1 also equals negative 8 because of symmetry. See how that saved me a little work? So that is our absolute max is going to be at x equals negative 1 and x equals 1 of the y value is negative 8. And then we will have a local min at x equals 0 and f of 0. Oh, that's easy. That's negative 9. That will be my local min. So we have a absolute max at x equal negative 1 and x equal 1 of negative 8. We have a local minimum at x equals 0 of negative 8. Nope, not negative 8, of negative 9. Okay, now we are going to find the second derivative, which I have done here. You use this form of the first derivative and find the second derivative. So I want to know, when is this equal to 0? I'm going to do something a little different this time. This equals 0 when negative 12x squared equals negative 4, or 12x squared equals 4. Divide both sides by 12, x equals 4 over 12, which is 1/3. So this will be equal to 0 when x squared equals 1/3. So that means when x equals the plus or minus square root of 1/3. So these are my zeros. Agreed? So I have negative 1 over the square root of 3 and positive 1 over the square root of 3. I know 0 is somewhere in here, and 1 is out here, and negative 1 is out here for testing purposes. So for testing, I will use this form of the second derivative. We're going to determine concavity and find the inflection points. So if I plug negative 1 into my second derivative, well, I always have this negative sign out here from the negative 4. But I plug negative 1 into the second factor, and that is positive. So overall, my second derivative is negative here, and the original function is concave down. Okay? If we plug 0 into the second derivative, I have this negative sign, and 0 would just be negative 1, so that's also negative. That gives me a positive, which means my original function is concave up in this interval, which agrees with what we have previously, but that's kind of hard to see at this step. Plug in 1. I have this minus sign out here. If I plug in 1 into that second term, that's positive. So overall, I'm negative, and I am concave down. So let's summarize this. We are concave down on negative infinity to negative 1 over the square root of 3 and positive 1 over the square root of 3 to infinity. We're concave up in the middle from negative 1 over the square root of 3 to 1 over the square root of 3. And where are my inflection points? Well, they're at x equal plus or minus 1 over the square root of 3. And we will have to figure out what the y value is by plugging those values into f. So let's see. All right, let's figure out the inflection points. We only have to do one of them because of symmetry. F of 1 over the square root of 3 is going to be equal to f of negative 1 over the square root of 3. Okay, so I have a negative sign, and I'm putting this and raising this to the 4th power. And this is squared minus 9. All right, 1 over the square root of 3. Maybe I'll do this up here. What is the square root of 3 to the 4th power? Well, that would be the same as 3 squared. This is 9. So this is negative 1/9 plus 2 times 1/3 minus 9. Now, I know this is not fun to do, but we can do it. Negative 1/9. 2/3 will be the same as 6/9. And 9, if I want to get a common denominator here, 9 times 9 is 81. So this, I pull out my handy dandy calculator and I ask myself, what's negative 82 plus 6, which I guess I could have done in my head. This is negative 76 over 9. So my inflection points look like this. Okay, now what do we do? We didn't answer this question. F is increasing on and decreasing on. We know it has a local and absolute max at x equal negative 1 and x equals 1. Had a local min at x equals 0 of negative 9. Sorry, that doesn't look like a 0 now. And this was negative 8. It is concave down. I don't have enough room. Concave down from negative infinity to negative 1 over the square root of 3. And from 1 over the square root of 3 to positive infinity, concave up in the middle. And let's see, I'm going to go back. We are increasing from negative infinity to negative 1 and 0 to 1. Increasing negative infinity to negative 1 and 0 to 1. So that means I'm decreasing from negative 1 to 0. Let's double check. Decreasing negative 1 to 0 and 1 to infinity. Okay, now we are just going to graph this thing. It's kind of hard to graph this one. Useful to know that 1 over the square root of 3 is approximately 0.6, so a little bit more than half. And then the negative would be a little bit more than negative 1/2. So those are these points here. This is my inflection points. And what is going on here? Well, this is the maximum right here. So this is what, I'm going to do a better job than that. Let's get these out of here. Okay, just so you know what's going on. The green, maybe that's a better way to do it, point here is at 0, negative 9. That's the local minimum. The orange are my maximums. They're local and absolute max. And then the inflection points are in red. So this is a minimum, and I'm concave up, and then I turn and become concave down, and I'm just sort of doing a little sketch, something like that. And then, of course, Desmos does a much better picture for us. So Here's my absolute max. Here's my local min. And in here are my inflection points. So I hope you work this problem for yourself. It's good to go through the whole procedure. It just really helps you learn it. Of course, you can do it a lot faster than I did in this video. But so good luck. Keep practicing. Remember, there is extra homework in the book. Okay, see you later.